Welcome to Math 31. This is a lesson on applications of extrema, part 2. So I'm going to go through a few more examples, and this will be broken into two video clips because some of them get a little lengthy. The first one, an open box is to be formed from a rectangular section of cardboard, like it says, given certain dimensions. So if you've ever worked in a bottle depot or anything like that, you might be aware of how boxes are formed. You could take this rectangular sheet, such as this, and then by cutting out squares in the corner, then you've got the sides that can be folded up, and then you've got a nice rectangular box, rectangular prism, I guess. And question, of course, is what length of the sides of a square will yield a box with the largest volume? So how much do you cut off to maximize the volume of this rectangular prism? And this one we want to take to the nearest 100th. And really what it comes down to is maximizing the volume, and V is equal to length times width times height. And the section we're going to cut off will be X, or you might as well make it X. It will be the same, of course, for each of them, otherwise you're going to have a pretty funny looking box, and you definitely will be wasting a bit of space. So you get all this, and we are aware that the entire length of this is 8 decimeters, and the entire width is 3 decimeters. So it actually works out pretty nicely that we can set out each of these variables, the length in terms of x, that is. So the length, which starts off being 8, is going to be 8 minus 2x, because you have the two pieces that are x units long. So this is going to be, when you fold the box up, it started off being 8, but you minus the 2x sides, and then the width will be done the same or very similar way. It's 3 decimeters now, but you also have to subtract 2x values. The height of this box is just x, the part that you fold up. So therefore the volume is going to be the product of these three. I'll put the x in front. 3 minus 2x multiplied by 8 minus 2x. And as always, want to be aware of the domain, if there's any restrictions on this. Now the x has to be greater than 0. You have to cut something off it, or else you do not have much of a shape, much of a rectangular prism, much of a box. You've just got a sheet of paper. But that's not it. We should also note that we have 3 minus 2x has to be greater than 0. Now this just makes sense. The width has to be, there has to be some width. So if the width is 3 minus 2x, 2 has to be greater than 0. So minus 2x is greater than negative 3. And then when you divide by negative 2, you'll get x has to be greater than, according to what I'm getting, x, let's make sense of this. Divide by negative 2x will be less than 3 over 2. Or let's call this 1.5. And don't think too hard about that. It makes perfect sense, right? If x is greater than 1.5, if you cut too much off, considering you've only got 3 decimeters for the width, it's impossible. And you're going to see for the other length part, 8 minus 2x has to be also has to be greater than 0, because you've got to have the height, some height. So negative 2x is greater than negative 8, so x is less than 4. And so you'll see when you take this all together, you're looking for numbers that are on one hand greater than 0, but on the other hand they have to be less than 1.5 and less than 4. So to simplify that, we would write it like that. So it has to satisfy all three conditions, so you don't have a number like 3, which is less than 4, but not greater than, but not less than 1.5. So we're in business. Now if you clean up this expression by foiling it, you'll get 24 minus 6x minus 16, so minus 22x plus 4x squared. And then distribute the x in. So v is equal to, I'll write this in descending order, 4x to the 3 minus 22x squared plus 24x. And then v prime as a function of x, I'll write this at the bottom, is equal to 12x squared minus 44x plus 24. So I'm going to get a little bit of space to work. So v prime at x, I'll write that out again, is equal to 12x squared minus 44x plus 24. Now, critical numbers. This is defined everywhere, so all we want is v prime at x equal to 0. Those are the only critical numbers we're going to get. So 0 is equal to 12x squared minus 44x plus 24. We might as well clean up this, I would, by dividing by common factor. Unfortunately, there's not that much we can take out of this one. Or there's nothing, we can't take out a factor of 12, but we should be able to divide out by a factor of, it looks like, 4. So if we do that, 0 is equal to 3x squared, make the factoring a little bit easier, minus 11x, divided by 4 is plus 6. And this one should factor into 3x and x, and then break that 6 down, and let's try a 2 and a 3. And then if we set this one up right, they're both negative. So minus 9 minus 2 is minus 11. We've got her. So 0 is equal to 3x minus 2 times x minus 3. When we solve both of these, I'm going to go directly to the answer. I'll get x is equal to 2/3, or x is equal to 3. Now what's interesting now is that this is the first time we've actually had to reject an answer for being outside of the domain, and that's why we have to pay attention to it. Now I know most of you, when you're solving this, if you got x equal 3, when you actually did try to work out the dimensions, you'd realize quickly that it's impossible. But I'll save you the trouble. This is to be rejected. This is outside the domain. Now I'm pretty confident that this is the right answer, and also that this is going to maximize. But just to be sure, is this a max or a min? Get in the habit of doing the second derivative test. So v, the second derivative, v double prime x, is equal to 24x minus 44. So the second derivative at x equal 2/3. Remember, all we care about is positive versus negative. So you can actually, with a calculator, you get this one pretty quickly. That'd be 8 times 2 is 16 minus 44. So that's negative 28. So v double prime at 2/3 is equal to negative 28. So therefore, the second derivative at 2/3 is less than 0. So negative, negative, that's going to give us the big scowly face like this. So there's a max at x equal 2/3. And we also want to, I did say to the nearest tenth for this one, oddly. We better get all the signs, all the other ones. So the height, when we divide it, is 2 divided by 3 is 0.67 decimeters. The width is equal to 3 minus 2 times 2/3. So I would just drive that right through the calculator, or get a fraction or get a common denominator. So 3 minus 4/3. You shouldn't really need a calculator for this one, but when you decimalize it, you will get that's equal to 1.67 decimeters. And then the length is going to be 8 minus 2 times 2/3. It's kind of the same thing. 8 minus 4/3 as a decimal is equal to 6.67 decimeters. And actually, if I'd read the question, those are the dimensions, but we don't really even need that. So cut off a section measuring 0.67 decimeters, and forget about the other stuff. But that'll give you the dimensions if you did want that for your information, just not necessary. So that's how these ones go. Now the next one looks similar. We have an open box with no top, and it's going to be constructed with a square base and with a total volume of this much. And here, though, we're getting some price amounts. The bottom costs this much, 3 cents per cubic or square unit. Sides that much. Get the dimensions that will minimize the cost of the box. And this time is an exact value. So you see the top is open. Now the difference with this one compared to the previous one was trying to maximize volume. In this case here, we're actually minimizing the cost. So it's not a volume. In fact, the volume is given. What we do want is the minimizing the cost, which is going to be related to the surface area. So first off, we want to look at the surface area, and I'll just write it as SA. It's probably easier. And the surface area is going to be equal to the bottom. There is no top. And as always, feel free to pause me and go through it yourself. And then the 4 sides. You've got the front, you've got the back, and you've got then the two other sides, left and right. And if you read this one carefully, the base is square, and that does make a difference. If the base was not square, obviously the slightly more complicated equation, although it could also be manageable. So let's see what we got. If we take a look at the illustration of this, I'm just going to call this side X and this side X. And then, well, the height, I guess, just H. So the surface area for that square on the bottom is just going to be X squared. And then the 4 sides, we've got 4 sides, and each of the sides would have area X times H, but there'd be 4 of them. So I'm going to try again to get this in terms of one variable. And that's where the volume comes into play, because the volume is just equal to length times width times height. So in this particular application, it's going to be equal to X times H, X squared H. So the height, given that the volume is 48 units, cubic units, it's going to be 48 divided by X squared. Now, when we put that in, we'll get surface area is equal to X squared plus 4 times X times 48 over X squared. So the surface area, if we did a little bit of mopping up on this one, is equal to X squared plus, well, the X will cancel, and then you just, so we just have the 1X, and then just multiply the 4 times the 48. So that should be, this should be 192. And then X on the bottom, but I'll write that as 192X to the negative 1, which eventually will make the differentiation easier. Now, before we get too deep into this one, don't forget the domain, and the simple aspect of the domain would be that X has got to be greater than 0. And I think that you'll see in this case that if you try to find a relationship for H, the height also has to be greater than 0, but that doesn't look like that's a problem. It too can be infinitely small, but bigger than 0, and it could be infinitely large. You just have a very unusual shape for this one. So X greater than 0 seems to be good enough. And we have to do one other thing. what I've got so far is the surface area, and like that question we did in the previous lesson where we had different price values, here we note that the bottom is 3 cents. So really a cost function based on all this would be C as a function of x is equal to the x squared. Well, all we do is we multiply this by 3 for the cents. So this cost function is in terms of cents. So 3x squared. And then the sides are 2. So plus 2 times 192x to the negative 1. So C as a function of x is equal to 3x squared plus, multiply that out, and you should get 384 x to the negative 1. So I'm going to bring up a new screen in just a second or two, differentiate this, and then see where it takes us. So C prime at x will be equal to 6x and then minus 384 x to the negative 2. So that's going to give you in a more convenient form to work with. C prime at x is equal to 6x minus 384 over x squared. Now the critical numbers are going to be where this is equal to 0 or where the derivative doesn't exist. And it will exist everywhere within the domain. X cannot be equal to 0, but that's not part of the domain. So I'm just going to go to this one quickly and solve this equation. So 6x minus 384 over x squared. Bring the negative term over, so 384 over x squared is equal to 6x. So notice again I didn't get a common denominator, just because I'm not doing any interval analysis. So this gives me 6x cubed is equal to 384. And then simplify this one, divide by 6. So 384 divided by 6 will give you 64. So x cubed is equal to 64. And then when you take the cube root, you get x is equal to 4. So before we go further with this one, I will check, is this a minimum or a maximum? Is the question. So second derivative test again. So the first derivative we've got. So the second derivative is equal to derivative of 6x is 6 plus, and then when you multiply your 384, watch your sign carefully because of course it matters. Negative 2 times negative 384 should be plus 768, and then x to the negative 3. I'm going to write down the bottom, x to the 3. And now we can see pretty plainly that when we do plug in 4, we will get a positive number. So 768 over 4 cubed. C double prime at 4 is greater than 0. So we're positive, big ol' smile. And then this is going to minimize the cost. So therefore, minimum at x equal 4. So the dimension, or I'll answer the question this time. The dimensions that will minimize cost are, well, base of 4 centimeters, and we better get the height. So before I get too deep into that one, h, as we saw earlier, is 48 over x squared. So h is equal to 48 over 4 squared. So 48 over 16, h is equal to 3 centimeters. And, oops, height of 3 centimeters. So that's how these ones go. Now I think we've got time to do one more. These ones are kind of nasty. And this is where we have the wire that is bent. So, just to keep things a little bit more confusing, I'm going to save that one for the next one, just to keep this video a little bit shorter, because that is actually the longest question in the bunch. So this might be a little confusing, but I'm going to wait for next time to do it, keep the suspense high, and instead look at this one, the inscribed object. And then that'll make for a more manageable question. You'll thank me when this is over. Inscribed objects is a wide variety of ones we can do, but we want to find the radius and height of the right circular cylinder of maximum volume that can be inscribed in this right circular cone with a specific radius and a specific height. We want to take this one as an exact value. So this is what we get. For whatever reasons, you're trying to put this cylinder inside this cone. And when it's inscribed like this, it means it's going to have to be in contact. And we want to get the largest, that is in terms of volume, cylinder possible within this. Now there's the height of the cone is 5 meters, and the radius itself is going to be 3 meters. So you could look at it like this. So there's 5 meters. And then the radius, which would be from this base radius there, r is equal to 3 meters. So this is a big cone. Now, the ultimate thing that we want is to get the cylinder with a specific volume. So don't forget or learn now that the volume of a cylinder is equal to pi r squared h. So you just take the area of the base of it and multiply it through the height of it. Now be careful, because that's for the cylinder, and of course the cone itself has got its own dimensions and its own formula for it. So make sure you make a good decision on that. Now the best way to tackle these ones is to take a look at this, a cross section of the cone, which is what that would be. Take out the third dimension, and there is actually half of, if looking just at the one half of it, that is going to be the cylinder itself. Now this is meaningful because this is going to represent the radius of the cylinder, and this is going to represent the height of the cylinder. And still having the same overall dimensions of this being 5 meters high, and then this being 3 meters. And if you use similar triangles, you can get a pretty good ratio set up. So this is not the sort of thing that would occur to most people when they first look at something like this, but it does work pretty well, because within this you've got actually two triangles. Now this would be the big one, and then this would be the small one. And the big one is, well, I've got the 5 already there, so is going to be 5 meters. Interesting. So this would be 5, good location, because that's going to be just the height of it, and then this would be 3 meters across the bottom. But this smaller section for the triangle is going to be this one right up there. And if you take a look at the dimensions, if this is 5, then if the whole thing is 5, and then this is h up to there, this is h, that top section is going to be 5 minus h. So that gives us the dimension there, 5 take away h. And then this bottom one, well, that's not going to be a problem because this is r right across the bottom. Or it will be a problem, but it's not going to be a huge problem. It's going to be a problem in that we have two variables. Now, what this is all about, by getting the similar triangles, we're still going to be maximizing the volume, but this will allow us to express h in terms of r, or in reverse. The equation will be easier if we go this way, though. So our ratio, you have a choice, of course, but I could write this as 5 over 3 is equal to 5 minus h over r. So cleaning up the fraction, 5r is equal to 3 times 5 minus h. So 5r is equal to 15 minus 3h. So 3h is equal to 15 minus 5r. So h is equal, divided by 3, is equal to 5 minus 5 over 3r. And then, I'm going to go back up to this formula. We can now say that the volume is equal to pi r squared. Instead of h, we can write that as 5 minus 5 over 3r. And then one last step on this page. I'll go 5 pi r squared minus 5 over 3 pi r cubed. And before we go any further, let's note the domain, because it was an issue in one of the earlier questions. And then the domain with this one, I think that we would all agree that r has to be greater than 0. And then the other thing, though, is that h has to be greater than 0. Now, it sometimes isn't an issue, but if you have a more complicated equation like this, then it may be. So 5 minus 5 over 3r has to be greater than 0, because that's what the height is in terms of r. So minus 5 over 3r is greater than negative 5. So when you divide by negative 5/3 and multiply by 3/5, you're going to get r is less than 3. So we actually have an upper limit as well. So 0 is a lower limit, and 3 is the upper. And of course, that makes perfect sense as well. There's no way, if the base radius of the cone is 3 meters, there's no way that we could have one larger than that. So we're good to go. I'm going to get some space, and then we're in the red zone and finish this one off. So just to write the volume out again so we can refer to this when we need it. So 5 pi r squared, I'm hoping I didn't forget this one, 5 pi r squared minus 5 over 3 pi r cubed. Take a quick peek back at that. Looks like we're okay. So differentiate in terms of r, and that will give you 10 pi r minus 5/3 times 3 is 5 pi r squared. Critical numbers. Once again, we don't have to worry about this not existing. There's no denominator or radical or anything like that. So we just set it to 0. And that's 10 pi r minus 5 pi r squared. Solve this one pretty neatly by taking out a common factor of 5 pi r. And that will leave you with 2 minus r. So 5 pi r is equal to 0. 2 minus r is equal to 0. So r is equal to 2. R is equal to 0. Well, r equals 0. Sorry, this is outside the domain. So the domain does matter. It matters more in some questions than others, but by training yourself to always look for the domain, even if it's sort of unnecessary, you won't be taken by surprise with a bad and nasty question. So v double prime, okay, let me explain what I'm doing. Is this a minimum or a max? You probably don't need me to remind you at this point. Let's do the second derivative. Second derivative as a function of r will be 10 pi minus 10 pi r. Intriguing. So second derivative at 2 is 10 pi minus 20 pi, so 10 times 2. So that's equal to negative 10 pi. I don't need to see any more. So I know this is a negative, so that's the sad face. So this is going to be a maximum, so therefore a max at r is equal to 2. So we better get the dimensions. The height will be equal to, well, we have that formula way back when, 5 minus 5 over 3 times 2. So when we work this one out, and I think we want exact values, we're going to get 5 minus 10 over 3. So when you work that one out, 15 over 3 minus 10 is also equal to 5 over 3 centimeters, excuse me. So the radius should be 2 meters and the height 5 over 3 meters. Kind of an unusual way to write a decimal figure, but just going by the rules, it's an exact value. So in the next part of the lesson, I'll go back and I'll do the one that we're missing in between, and then I will do the remaining ones on that lesson. So thank you for your time.